Hi everybody, this is lecture 11 about solids, liquids, and gases. So first let's talk about what a solid, liquid, and gas is. So a solid is closely packed particles, rigid, often with a crystal structure, definite shape and volume and high density. So that's this situation right here. There's a box. There's a solid right here in the corner. Okay, made up of atoms here. It doesn't fill the container, and it doesn't take the shape of the container like a liquid. Liquid is the same thing as a solid. It's closely packed particles, but it's got no structure. So it's got a definite volume, but no definite shape. It has high density, but often lower than for solids. So this is the example of liquid. This is the container. Notice it doesn't fill the container. It's got a definite volume, but it takes the shape of the container. Then gases are particles that are spread out. There's no definite shape, no definite volume, and they're low density. So this is this situation. We have a container, and the gas particles fill the container. So not only does gas take the shape of the container, but also takes up the volume of the container. And it's much lower density than solids or liquids. Okay, the crystal structure. This is a regular arrangement of atoms in a crystal. And this is how a lot of solids arrange themselves. This is a complex thing where there are many types of crystal arrangements that different atoms and elements can form. So it's complicated, but a lot of solids come in this crystal structure type. One way we figured out that atoms do arrange themselves in crystal structures is we shoot X-rays at them. The X-rays scatter off the crystals. We measure those scattered photons, and we can backtrace where that scattering came from and give us a pattern of crystal structure. And this was originally done by these guys named Bragg. Okay, density. Density of something, solid, liquid, or gas, is how much mass it has per volume. So a lot of the units for this would be grams per cubic centimeter or kilograms per meter squared, meter cubed. Okay, and the density depends on the mass of the atoms and the spacing between the atoms. So density is a property of the material. Okay, so like gold right here is very, very dense, and feathers right here is very, very not dense. Okay, elasticity is an object subjected to external forces may undergo changes in shape or size. Okay, that happens to everything. But a body's elasticity is a measure of how much it changes when a deforming force is exerted on it and how well it returns to its original shape. So of course I can exert a force on anything and it might just break. But if something, I exert a force and it comes back to its original shape, then that thing has elasticity. So materials that do not return to their original shape are inelastic. And then we have the modulus of elasticity, which describes elasticity behavior. Okay, which is more elastic, steel or rubber? What we mean by more elastic here is which one has a larger force that it can handle and still stay elastic. So obviously rubber is very elastic because it can stretch, but it can't handle much force, whereas steel can handle lots of different forces, very, very high forces, and still hold its shape. So that would be steel. Okay, tension and compression. If we put tension on materials, then, okay, so we got a beam here. If we put a heavy block on the side here, then the top has extension under tension, and the bottom side has compression. In this situation, if we put a beam like this with some supports, we put a load on top here, then the top gets compressed and the bottom goes under tension. Often buildings use I-beams to put more material on the top and bottom to be strong against this extension and compression. Okay, suppose you drill a hole horizontally through a tree branch as shown. Where will the hole weaken the branch the least? Well, that's in the middle. The middle doesn't change much. It's the top and the bottom that feel extension or compression. So we want to do it in the middle. Okay. So arches. Arches use well, let's read it here. If So they used to have to do supporting columns, then the discovery of arches made use the compression of stone to hold weight. If an arch is supported only by its own weight, then the proper shape is a catenary. And that's like an example of the St. Louis arch. So arches take advantage of the capacity of stone to withstand compression. So there we go. Okay, pressure. The idea of pressure is force per area. Okay, and so if we have a large force but a large area, the pressure could be low. If we have a small force but a tiny area, the pressure could be high. So it's the ratio between force and area. And the unit is the Pascal, which is a Newton per meter squared. So that's a force per area. There's other units such as feet, pounds per feet squared, pounds per square inch, torr, and others you'll hear. They're all pressure. Okay, so here's an example of the idea of pressure. This teacher is laying on a bed of nails. Even though the surface area for each individual nail is small, the total surface area for all the nails is large enough that it doesn't hurt her at all. Okay, when you stand on one foot instead of two, the force you exert on the floor is the same. You have the same weight. Weight didn't change. Okay. When you stand on one foot instead of two, the pressure you exert on the floor is more. Because now you have the same weight on less surface area. Liquid pressure. Okay, so liquid pressure is how much force the liquid can exert on something immersed in it. So force per unit area that a liquid exerts on an object depends on the density of the fluid, does not depend on the volume of the fluid or the shape of the container, acts equally in all directions, and it depends on the depth. So it doesn't depend on how much water there is, it depends on the depth of the water, and that's it. Okay, water pressure provided by a water tower is greater if the tower holds more water? No. Is taller? Yes. Only depends on the depth. So it's going to be A. Okay. Okay, the displacement rule. The displacement rule says a completely submerged object always displaces volume of liquid equal to its own volume. So if we immerse this rock in liquid, it pushes its volume of liquid out of the beaker. The buoyant force, buoyancy, tells us that the higher the pressure on the bottom of the object exerts a net upward force. Okay, so when you put an object in a liquid, there's going to be a supporting force and a supporting forces all along the object that overall is going to try and make the object float. How many forces act on a submerged body at rest in a fluid? Oh, buoyancy acts, that's true. 2, buoyancy and a force due to gravity, that's true. None. Oh well, it's not true. We definitely have buoyancy and gravity, so I think B is the best answer. Okay. So buoyancy. Buoyancy is the floating force, tries to push something up and out of a fluid. Most of the time, water. Okay, so will something sink or float? If the buoyancy force is high and the force of gravity is low, then it'll float. If the force of gravity is more than the buoyancy force, then it'll sink. And this all has to do with density. So if something's in water and it's less dense than water, it'll want to float. If something is in water and it's denser than water, it'll want to sink. Okay. Cook who measures a specific amount of butter by placing it in a measuring cup with water in it is using this displacement rule. Okay. Archimedes' principle says, right here, the buoyant force is the weight of the displaced fluid. Okay, so if we have a 3, let's look at this example down here. So we have a 3, let's call this grams. That's probably too little. 3 kilogram, let's do kilograms. 3 kilogram metal thing. And we've got nothing over here. So it's reading 0. If we now put this into the beaker and it pushes out 2 kilograms of water, then this device will read 1 kilogram. Because it's a 3 kilogram weight, but it's feeling a buoyant force of 2 because that's the weight of the water it displaced. So overall, it's left with an apparent weight of 1. Okay. When a fish expands its air bladder, the density of this fish decreases. It gets bigger, same mass, so its density decreases. When a fish makes itself less dense, the buoyant force on it, well, if it's making itself less dense, it's probably decreasing its volume. If it decreases its volume, it's displacing less liquid, which means the buoyant force decreases. I misread that. Less dense. When it makes itself less dense, it's probably increasing in volume, which means it's displacing more water, which means the buoyant force decreases. When a fish expands its air bladder, the density of the fish, we just read that. When a fish makes itself less dense, the buoyant force on it, so it's probably going to make itself less dense by increasing in volume. When it increases in volume, then that's displacing more water, which means the buoyant force increases. Okay. You place an object in a container that is full to the brim with water on a scale. The object floats, but some water spills out. How does the weight of the object compare to the weight of the water displaced? Well, according to this picture over here, this wood block pushed out the amount of water equal to its weight so that it can perfectly float. So if we were to measure the mass that it had displaced, the weight of this would be equal to the weight of the block. So I think that means the weight of the object is greater than the weight of the water displaced. I don't think so. Weight of the object is less. I don't think so. Weight of the object is equal to the weight of the water displaced. I think that's the right answer. Although it says A here, I think C is the right answer. If you have any questions about that, please come to office hours. Okay, so buoyancy in air. Since air is also a fluid, it also has a buoyant force. We have Bernoulli's principle, which says if something moves faster, its pressure drops. If something moves slower, its pressure increases. Okay, and this is what allows planes to fly. Okay. The pressure in a stream of water is reduced as the stream speeds up. Can a stream of water from a fire hose actually knock a person off his or her feet? Okay, so these are two things. One is the pressure in a stream of water depends on the speed of the water. However, if the water jet hits you directly, then it's changing the momentum of the water, exerting a force on you using another principle, which is definitely going to knock you off your feet. So it can, and it's consistent with Bernoulli's principle. Let's see what it says. It can, and it's consistent with Bernoulli's principle. Okay, they're really two different things. There's a difference in the pressure within a flowing water and the pressure it can exert when its momentum is changed. That's the important part. Surface tension. Okay, surface tension. Liquids try to hold themselves together at the top of a liquid. The surface is trying to hold itself together. And that's what we call surface tension. Capillary action is when you have a narrow pipette. Then liquid wants to siphon its way up it by climbing the walls. This is due to adhesion between the molecules in the liquid and the walls that are part of the pipe. Okay, the atmosphere, the Earth's atmosphere, it is much less dense and much lower pressure high and much higher pressure and much higher density at sea level. Okay, and it's held in place. Its container is gravity. Keeps things warm and alive, that's for sure. Its molecules in constant motion. It's about 25 miles thick. Okay, atmospheric pressure. Well, that's how much pressure is at what we're feeling right now, which is about 14 pounds per square inch, or about 100,000 pascals. And this is due to the amount of air that's holding the height of air above us that is weighing down on the atmosphere where you're sitting right now is causing that pressure. And we can measure pressure with barometers. Okay, the normal way to do this would be with water or mercury traditionally. But there are other ways we can do this with other devices. Okay, here's some examples. There's Boyle's law, which gives us the relationship between pressure and volume. If volume goes up, pressure goes down. If volume goes down, pressure goes up. Okay, a piston in an airtight pump is withdrawn so that the volume of the air chamber is increased 3 times. What is the change in pressure? Well, 3 times the volume goes up, means the pressure goes down by 1/3. So B. Okay, so there's Boyle's law. Pressure and volume have that inverse relationship. There's other gas laws. There's Guy-Lussac's law. It says if temperature goes up, pressure goes up. If temperature goes down, pressure goes down. There's Charles's law. It says if pressure is constant, if volume goes up, temperature goes up. And if volume goes down, temperature goes down. And then there's Boyle's law. We can put these together into a combined law. Okay. The crystals that make up minerals are composed of atoms with a definite geometrical arrangement. That sounds good. Okay. Which of these has the greatest density? 10 kilograms of concrete, 2 kilograms of concrete. Well, those are the same. Different masses, but same density. 3 kilograms of iron. That sounds more dense than concrete. And lead, that's even denser. Okay. When a given mass of water freezes, it undergoes a decrease in density. Becomes from a liquid that's very dense to a vapor that's not dense at all. A lasting material is one in which stretch is achieved for relatively small forces? Maybe. The original shape is restored when deforming force is removed. That sounds right. When dropped, bouncing to practically the same height as it achieved, well, that's like a elastic bouncy ball, but that's not necessary. Internal tension is relatively small. That may or may not be true, so the second one is the best answer. When you sit in the middle of a horizontal bench supported at its ends, the top side of the bench is, well, if we go back to, where's that picture? This picture, that's us sitting on the bench. So bottom is under tension, top is under compression. Let's see if I can find this here. So the top side is under compression, we said. Under tension, and the bottom, the top side of the bench is under tension, and the bottom side is under compression. That's not right. The top side of the bench is compressed, and the bottom side is stretched. That sounds right. So I think it's and compressed, and a neutral region in between is compressed. I'm not sure that makes sense with the second one. Okay. Opposite flanges in a properly positioned horizontal I-beam supported at each end undergo. Well, this is a similar situation. It's going to be compression in the top, tension in the bottom. Okay. The strength of a stone arch is due to tension between adjacent stones. There's no tension, it's all compression. Compression between the adjacent stones, that sounds right. Okay. When you stand on tiptoes on a bathroom scale, there's an increase in, not weight, same weight. Pressure, well, it's different surface area because you're lowering the surface area when you go on your tippy toes. Same weight, which means higher pressure. So there's an increase in pressure, but that doesn't register on the scale because it's measuring weight. So I think it's the second one. Both weight and pressure on the scale, that's not true. So the second one. Sarah lies on a bed of sharp nails. The pressure of each nail against her body is less with more nails. More nails, more surface area, less pressure. Water pressure at the bottom of a lake depends on it doesn't depend on the weight of the water, because it could be a big lake, that's a heavy lake. It could be a small lake, that's a light lake. Doesn't matter. Surface area of the lake, that doesn't matter. What really matters is the depth. The depth determines the pressure. Okay. Consider 2 tubes filled with water at the same height, one with fresh water and the other with salt water. The pressure is greater at the bottom of the tube with, well, we know salt water is more dense than fresh water. So since salt water is more fresh, if they have the same height, then the one with the salt water will have the higher pressure. If a hole is punched in the side or the bottom of a boat, water spurting in will be perpendicular to the surface of the boat interior in an upward direction in such a way to minimize flow rate conserved. I think the best answer is the first one, perpendicular to the surface of the boat interior. Okay, because if it's upward, it's only going to be if the puncture's in the bottom of the boat. If it's in the side of the boat, it's going to come in sideways. So it's always going to be coming in perpendicular to the surface of the interior. Buoyant force on a submerged object acts in an upward direction because the force is opposite to that of gravity. Well, that's true. It moves in a direction towards floating, which can only be upward. That's also true. Upward pressure against the bottom exceeds pressures elsewhere on the object. That sounds like the best answer. The density of water increases with increasing depth. That's not quite true. Mostly not true. So I think this one, third one's the best. Okay. The buoyant force that acts on a 20,000 Newton ship is, well, if the ship is just sitting there, it's in equilibrium. So the weight on the ship is 20,000 newtons. So the buoyant force must be 20,000 newtons. So the second one. Okay. When a 20,000 Newton ship passes from salt water into fresh water, the buoyant force on the ship, well, if it passes from salt water to fresh water, we know that salt water is more dense than fresh water. So that means that the boat is going to sit lower in the water to displace more. But because it's floating there and the weight is 20,000 newtons down and it's in equilibrium, it's not going anywhere, then the buoyant force will still be 20,000 newtons. So it remains unchanged. Okay. When you float in salt water rather than fresh water, the volume of water displaced it's going to be less because salt water is more dense. So less and the buoyant force is unchanged. That sounds good. Less and the buoyant force is more. That's not right. Unchanged and the buoyant force unchanged. That's wrong. It's got to be less and the buoyant force is unchanged. Okay. The buoyant force that normally acts on a fish in water is slightly less. Well, a fish swimming around. Right. The weight force on it will be down and the buoyant force will be up. Assuming it's not floating or sinking, it's just swimming at a neutral way, then the buoyant force and the weight of the fish should be the same. So it should be equal to its weight. Okay. Compared with the buoyant force that acts on a submarine floating at the surface. When submerged, the buoyant force is, it's going to be more. Because part of the volume of the submarine when it's surfaced is sticking out of the water. When the entire thing is submerged, it's displacing the maximum amount of water possible, so it's going to be more. Okay. Consider an air-filled balloon, weighted down so that it's just barely able to float on water. If you gently push it beneath the surface, the density of the balloon, well, it's filled with air, this balloon. And when the pressure increases on the balloon, it's a gas. Knowing from those gas laws we have, that means the volume is going to decrease, which means the density of the balloon is going to increase. So density of the balloon increases. As a swimmer dives deeper and deeper, buoyant force on the swimmer actually... Okay, so as a swimmer dives deeper and deeper, the buoyant force on the swimmer actually, well, the swimmer probably has air in their lungs, and they have some elasticity in their body. So they're gonna get slightly smaller, which means we're going to displace, if we keep going down, we're going to displace less liquid, which means the buoyant force is going to reduce. Probably very slight, but it's probably going to reduce. Okay. Surface tension in water is due to adhesive forces. Okay. Two solid blocks of identical volumes are submerged in water. One block is lead, more dense, and the other is aluminum, less dense. Upon which is the buoyant force greater? Well, they're identical volumes. That means they have to have this, they displace the same amount of water, which means they have the same buoyant force. So it's the same on both blocks. Now, because the lead is more dense, it's going to sink faster, but same buoyant force. Okay. Molecules that make up Earth's atmosphere don't fly off into outer space because of gravity. Atmospheric pressure is caused by the atmosphere's, well, we know it's the column, it's the depth of the liquid that causes the pressure. So in this case, we're talking about the weight of above in a column of air imagined. The higher one goes in the atmosphere, the less the atmospheric pressure. That's true. Less the density of air. That's true. So both of these. Okay. The weight of a 1 square meter column of air extending from sea level to the top of the atmosphere weighs about, well, we know the atmosphere is about 100,000 pascals, and that a pascal is a Newton per meter squared. So 100,000 pascals is 100,000 newtons of air on 1 square meter. There we go. Barometer can be used to measure, well, atmospheric pressure. I think that's the best answer, but it's going to be both of these. Altitude with some knowledge of how the atmosphere works, but it directly measures atmospheric pressure, and from that we can deduce altitude. Okay, simple barometer will be the tallest if it uses mercury, water, gasoline, or any of these liquids for the height would be the same at sea level. That's not true. So the pressure that we're measuring is the same for all of these, and the less dense one will have the higher column. So that's going to be gasoline. If a hot air balloon hovers at a fixed altitude, the net weight of the balloon must be, well, if they're at the same, if a hot air balloon is hovering at a fixed altitude, that means the weight force and the buoyant force are equal, canceling each other out, and the hot air balloon is in equilibrium. So slightly less than the weight of the displaced air. Equal to the weight of the displaced air, that sounds right. Slightly greater, no, it's going to be the second one. As water in a confined pipe speeds up, the pressure it exerts against the inner walls of the pipe, well, we know as speed goes up, then pressure goes down. So it's going to be decreases. Compared with the pressure within the water coming from a fire hose, the pressure that can knock over a shed is more. If air speed is greater along the top surface of a bird's wings, the pressure of the moving air there is, well, if airspeed is high, that means pressure is lower. So it's going to be less. Okay. And that's it for today's lecture. I'll see you guys next time.